Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss classification of conductor, semiconductor and insulator on the basis of band gap. Let's begin. Inside the crystal that is the combination of a group of atoms that are arranged in an infinite array basis plus lattice. We observe crystal. Inside that of crystal, each electron has a unique position and no two electrons see exactly at the same pattern of surrounding of charges because of this region. As two electrons, we can't see exactly the same pattern of surrounding charges. Each electron will have a different energy levels. Due to that reason, each electron have a different energy levels, and these different energy levels with continuous energy variation is known as the energy bands. These different energy levels with continuous energy variation form what are called energy bands. So, what is energy level and what is energy bands? Combination of energy levels, we call it as energy bands. The energy band which includes the energy levels of valency electrons. The energy band which includes the energy levels of valency electron are called valency band. Similarly, above that valency band there will be an energy band that is known as the conduction band. Let me take energy bands which includes the energy levels of valency electron, that is known as valency band. VB. Above that valency band there will also an energy band that is known as conduction band. In between these two bands that region is known as forbidden band. Forbidden band or forbidden gap. No energy levels are allowed within that of region, and the energy possessed that band gaps is known as forbidden energy state, and which one is denoted by E of G, that is forbidden energy state. Now, we can easily classify conductor, semiconductor as well as insulator by taking that energy bands. For conductor, there is no energy gap, means E of G is equal to 0 electron volt. Now, it is easy for the electrons to be available for the conduction on the application of external field in any form, the external electric field in the form of either electric or heat. The electrons shifts from valency band to that of conduction band. So, this type of solids are called conductors. An example of conductors: cadmium, zinc, barium, etc. In case of conductor, that will be the valency band, and here one is the conduction band. These two bands are overlapped with each other. Therefore, E of G is equal to 0 electron volt. That is known as conductors. It is easy to move electrons from that of valency band towards that of conduction band in order to conduct electricity throughout that of particular crystal or metal. Next, insulator. In case of insulators, there is no free electrons, and the all energy bands are completely full in that of valency band, and conduction band is entirely vacant, no free electron. All energy bands are completely filled in valency band, completely full in valency band, and conduction band is entirely vacant. In case of insulator, there is a large forbidden energy gap between valency band and conduction band. For insulator, that is valency band, that one with the conduction band. The forbidden band gap and the energy required to transfer an electron from valency band to that of conduction band is the forbidden energy gap, that is Eg, which is much more greater than 6 electrovolt in case of insulators. In insulator, there is always forbidden energy gap between valency band and conduction band, large forbidden energy gap. It is practically impossible to excite any electron across that of forbidden band, as that band gap energy for insulator is approximately 6 electrovolt. The examples of insulators are wood, cloth, glass, mica and quartz. These are the examples of insulators. Insulators, on the basis of band gap, we classify it: no free electrons, valency band completely filled, whereas conduction band entirely vacant, and the forbidden energy gap is too high, which is greater than around 6 electrovolt, and it is practically impossible to excite an electron from valency band to that of conduction band. Next, for semiconductor. For semiconductors, these are the solids where the band gap energy is very small, that is of order of 1 electrovolt. If we take valency band, conduction band, and that band gap energy which is very less, around 1 electrovolt in case of semiconductors, that means which can be overcome by the application of external electric field or raising the temperature. If we either increase external temperature or we apply an external electric field, then that forbidden energy gap which is very small, means the order of 1 electrovolt, can be overcome. For that of case, at 0 Kelvin temperature, the valency band is completely filled and the conduction band is fully empty, and at this temperature the conductor just behave like as an insulator. At 0 Kelvin temperature, in case of semiconductors, since the valency band will be completely filled and conduction band completely empty, therefore at that 0 Kelvin temperature that semiconductor behaves like an insulator. We classify that semiconductor into two ways on the basis of their doping. One is intrinsic semiconductor, another one is extrinsic semiconductor. In case of intrinsic semiconductor, that is a pure semiconductor in which no impurities is added. Examples: germanium, silicon are under that intrinsic semiconductor, pure type semiconductor. In case of extrinsic semiconductor, which is doped one, it is doped with suitable impurities. And again that extrinsic semiconductor is classified as two types. One is N-type semiconductor and another one is P-type semiconductor. So, what is N-type semiconductor? In N-type semiconductor, the impurities is pentavalent impurity. Here pentavalent impurities are doped, are added. Example of pentavalent impurities: arsenic, antimony, phosphorus, bismuth, etc. are the examples of pentavalent impurities. Again, in case of P-type semiconductor, here we use trivalent impurities. Here trivalent atoms are doped as impurities, trivalent impurities are added. Example of trivalent impurities: boron, aluminium, gallium, indium, etc. are used as trivalent impurities in case of P-type semiconductor. Let we add pentavalent impurities to that of pure semiconductor in order to achieve N-type extrinsic semiconductor. Taken arsenic, which one is pentavalent impurities? that is doped with pure semiconductor silicon. Let for silicon, 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 four, 5, 6, next electron, 1, 2, 3, 4, 5 electron, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 3, 4, 5, 6 electron, 1, 2, 3, 4, 5, 6 then electron. Arsenic, pentavalent, 1 electron, 1 electron, 1 electron, 1 electron. There are 4 electrons in order to form 4 covalent bonds, but another electron will be there, and that electron is nothing but free electron, and that free electron is used for conduction purpose. Similarly, for p-type semiconductor, trivalent impurities are used. For trivalent impurities, let we prefer indium, indium that is doped with silicon. So silicon, 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 1, 2, 3, 4, 5, 6, 1 electron, 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 and it has trivalent. So trivalent 1, 2, 3 electron. There will be a deficient of 1 electron, and that electron can be fulfilled by silicon-silicon bond, and this is the formation of hole. Here hole is formed. So the bond that one is hole. Here hole is the charge carrier in order to conduct electricity in case of p-type semiconductor. Here free electron are the charge carrier. In this way, with the help of this particular video lecture, we understand the concept of conductor, semiconductor and insulator on the basis of band gap. What is energy levels and energy bands? Next, valency band, conduction band, valency band, conduction band, forbidden energy state. On that basis, we classify conductor. Examples of conductors, we show it in terms of valency band and conduction band. Insulators, examples of insulators. Next, semiconductor, properties of semiconductor, classification of semiconductor as intrinsic and extrinsic. Intrinsic pure one, extrinsic we used impurities in the form of doping. It is of two types, one is N type, another one is P type. In case of N-type, pentavalent impurities are added. In case of P-type, trivalent impurities are added. Pentavalent impurities examples: arsenic, antimony, phosphorus, bismuth, and we show free electron as a charge carrier in case of N-type semiconductor. And in P-type, the trivalent impurities like boron, aluminum, gallium, indium, etc. And here is the deficient of one electron, and that deficient can be overlooked by the formation of a hole. Hole is the charge carrier in case of P-type semiconductor. So, with this useful and informative notes, let me wind up this session. Thank you.